lecture by Spencer Cattalani, a graduate student from Stony Brook University. He used to be the librarian for Math Club, and now he's a grad student. I guess that's an upgrade. Thank you very much.
Thank you. So this talk is on surfaces, and you know, surfaces are like everywhere, right? Like the surface of this desk is a surface, but then you ask somebody to draw a surface, like especially in a math class, and they do this. Right? Have you seen this? So if you ask somebody to draw a surface, they draw something with some number of holes. This is because, okay, there's this famous theorem that all closed surfaces look like this. But this is boring, right? And then this makes it seem like that theorem has nothing to it. Because if you draw a surface, you draw it like that. So you're like, okay, well then what's the content? So let me draw an adequate picture of a surface. This is a surface. You see, these are like little boundary circles. So this is like if you had some kind of surface cut off parts, there's holes in it. And it's all like gross and ugly. It's like, in general, a surface should be like if you like, I don't know, are doing surgery, like you open somebody up, they're like inside of a person is a surface. So like you could not tell me how many holes that surface has. It's like super complicated, right? And then, you know, it doesn't even have to be one piece. Be in pieces, right? Super bad. So, the way I came into the topic of this talk is I didn't like the proof of the classification of surfaces I read. So there should be one that like, there should be a better one. So I started looking for one. And it turns out that it's like, maybe not so difficult if you have like the right techniques. So the techniques that justify the pictures I'm going to draw are a little bit difficult to show, so I won't like prove them. But they're more or less believable. And then the connection to physics is if you think of these as being like particles or whatever. These like little boundary circles. And then as you go along the surface, stuff happens. So you have these two particles or whatever. As you flow forward in time, they like collide. Become one particle, stuff happens. Then you get that a surface is kind of like a description of a physical system. And then if you can talk about surfaces well, then you can talk about physical systems well. So that's what the second part of the talk is. Any questions so far? Yeah?
What makes you not like that drawing right there? Is it because it's too complicated?
This drawing? Oh, why don't I like this? Well, it's not bad. I mean, this one's maybe bad because it's boring, but at least I can like recognize it. So if you see this like on the street, you're like, okay, it's a surface with like two holes, right? This, it's not at all. It's like super complicated. And then, if you want to maybe understand it, you have to straighten it out, right? So that's what we'll try doing. So, like, we're actually gonna like straighten this out. So, this has some number of boundary circles. Let's like have a table down here. Some kind of table, right? And then we pin them to it. And then there are some on the bottom here, but then there are some that go upward. So then we like hang them from the ceiling or whatever. And then a bunch of stuff happens in the middle. So we've done the first step. I think these probably aren't the same thing, but the idea is you, just because it would be very difficult to keep track of all the different features, right? You start with this surface, and then you just kind of put all the boundary on these two little planes to get stretched out. Does that make sense? It's like a topological thing right here. Yes?
Does it matter which boundaries we connect way, or does it just matter that we can match one to each? You know what I mean?
Yeah, so I was thinking about this when I prepared the talk because, because it seems arbitrary, and it is arbitrary. So it doesn't even matter. You could put them all on the table, but it kind of undermines the idea if you put them all on this bottom table. The idea is you want to arrange all the bad things by height, and then it makes it easier to work with. So it's nice if you have some kind of reason to have height, so you stretch it out on some screen. You see, if you let me. So we have these things, like this little bulge or whatever. But then it doesn't really do anything. I mean, topologically, you can just kind of shrink this in. And then, really this happens a lot. And then this, this tube is wiggly. But I mean, that's no big problem. We can, straighten it out, right? So all the interesting stuff, all the difficult stuff, happens kind of when you hit like one of these things. So these on a surface, they look kind of like this. Like a saddle. So it's called a saddle because that's the shape of a saddle. So think, you have the part where your legs go and that goes down, and then you have the part that goes on the horse, and that goes up. So you have two things that go in different directions. And so these are like saddles, and then you can have hills, and then you can have where all directions go down, and then cups, where all directions go up. And these, if you look at, say this is smooth, if you take the height function, these are the critical points. So the critical points of the height function are where all the interesting stuff happens.
What's the height function?
So if this is like 0 to 1, the height of this point would be like 0.8, right? See how this function. The prototypical example of this is if you stand a donut on end, and you take the height, then the critical points of the height where the derivative vanishes are here. And if you go up, this is, you know, you go here, nothing, 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 nothing. Then you hit a point, and then you get circles that widen. So you look at these cross sections. And then it splits into two circles, and this is something interesting. And then it's two circles for a while. And then up here, they rejoin into one circle. Up here, back to a point. So by looking at these cross sections, you can see where all the interesting stuff happens. And then it's the same as these little things. Does that make sense? It's kind of a big step. Yeah?
So in other words, you can actually measure each of the, or how long each of the circles are at each part of the donut itself.
What do you mean?
What I mean is, like, for each, how do I put it, for each slice of the donut, I guess you could say, you can measure how long that slice is. I guess you could say, you know.
Yeah, so you can, but because we're working topologically, it's not, it doesn't matter so much for the discussion. So what really matters is when the cross-section changes shape completely. So when it goes from one circle to two circles.
Okay.
Okay, so,
I have a question.
yeah.
So what's geometric interpretation of their height function again?
Like the actual geometric, like, I mean this, if you think of it as actually just standing up,
Alright.
all the things with, if this is 1/2, standing up, you have a ruler to the side,
Mm-hmm.
then everything along this line has height 1/2. It's like just actually measuring like height off the ground.
Can you just classify your surface based on like how many times it splits? So if you know, like if you have one critical point, you know it splits into like two pieces, or maybe you'd have to look at it because I guess if it was a sphere, it would also have two critical points. But you can see how many times it splits when you classify it like that. And what if you have a projective plane?
Yeah.
What does that look like?
So, yeah, so here's the problem. This has 4 points, right? 4 critical points. So does this. So then one of the important things is that, well, this is a cup. This is a saddle, this is a saddle. This is a cap, right? So that matters. So here it's 2 cups, 2 caps. But then you can also have this problem of let's just do this. This is a sphere, but we've introduced these like 2 things that kind of cancel out. So there are some problems with that. And then the real projective plane, that's difficult because it doesn't embed well in space. So I couldn't, draw a good picture. And then it's not orientable.
It sounds super important for the classification of surfaces, and like don't worry about it.
Okay, no, but this will work for oriented compact surfaces, are the assumptions. Okay, so we have that, so I was thinking about whether it's a saddle or a cup, that matters. So if we take our stretched out entrails or whatever, we just want these to be at different levels because that'll make the picture clearer. So let me. So this is not the same surface. But the point is that now all the interesting stuff is on different levels. So we can now do this fantastic step where we just kind of cut between the levels. So the idea of cutting between the levels is that all the interesting stuff happens here. So nothing interesting should happen between here and here. So then if you're building your thing out of blocks, you just want to add one interesting thing at a time. So if you cut between these interesting, or if you cut between them, then you'll have that. You'll be adding one interesting thing at a time. So if we look here, this little piece that we have from the first one looks like this. And then this one looks like this. This one looks like this. It's like a little hemisphere. This one is just this one again. And then this one, upper hemisphere. Does everyone see how you get these from the picture, right? So then the steps are, you take this unimaginably messy thing. Since, you take all the ends and then you stretch it out. So it has a nice, it's all stretched out. And you have certain interesting things happening with respect to height. So we've gone from this and we've gotten some information by stretching it out. And then we just move these around. Like with your hands or whatever, pull this one down. And then you get all the interesting things happening at different levels. And then you cut between them. You get that everything is made out of these four pieces. So in a few words, yeah?
So you're trying to divide in your surfaces into like destroying part of the process, like algebraically. So what happens if you have two critical points at the same height? How would you identify that?
What do you mean if you have two different points?
Like when you do the counting stuff, right? If there are two critical points at the same height, how would you divide them?
I see. You just you just push one up and then cut between it. And so you just kind of move the other one up in space.
You need five of them, like the ones that are in the green chalk.
This?
Yeah, 1, 2, 3.
This one is just this one.
I
They're like the
Yeah,
same
I
piece.
understand.
Yeah.
got
Okay, so then if we work backwards, say we have these 4 pieces, then we can go along and glue them together to get any kind of shape, any kind of surface. Yeah?
The order matters, right? The order you glue them, it doesn't matter.
So we have no reason to expect that it shouldn't matter. I mean, off the bat, we should think it matters, and then part of the point is that we can later see that it doesn't matter completely. So, for instance, here's one way it matters. If you glue this to this, the 2 different ways to do that are and these are different, because this one has a hole in it and this one doesn't. So that's one way. So we'll sort it out and see the ways in which it matters.
There's 2 critical points and you push one to the other, then.
Oh, if they're like if you have 2
Yeah, like.
critical points at the same level, it doesn't matter if you bring one up or down. It doesn't. Okay. So you have these 4 elementary pieces, and then you can get any surface by gluing them together. And then we want to see what ways of gluing them together yield the same surfaces. Does this make sense to everyone so far? Okay, so we've gone from this picture to 4 things that we'll glue together. These have names. So this one is called 1, like the number 1. This one is called, you can either call it times or mu, but we'll just call it mu for now. This one is delta. Is that a delta? Yeah. And then this one is E. Or epsilon.
I have a question.
Yeah.
What's the difference between mu and delta? They're topologically the same.
Yes. Okay.
Can you consider like one is the inverse? I don't know.
So they're dual to each other.
You also
So they are, and these are topologically the same, right?
yeah.
But if we glue them going upward,
Okay.
so if you like, say these are like particles or whatever, and you go forward through time, this is one particle splitting into 2. This is 2 particles colliding and becoming 1. Or, you know, you think of them as like circles doing that or whatever. So because we're arranging them in height, they're different. And this is actually where this is like the step where all the interesting structure comes in. So let's start with this mu. So does everyone see topologically how this is true? You just pull this loop up and this loop down. You get that these two things are equivalent.
What does that symbol mean right there, the equal sign with the above squiggly line?
Oh, it just means like essentially the same.
In other words, topologically equivalent.
Yes. Yeah. Yeah.
So how would you define this your surface? You define it to be mu plus mu, or like just mu plus mu? Like you see what I mean? How do you define these two surfaces with the elements you have?
I see.
Can I consider it as a group operation or something?
This is exactly it. So the exact point, and then also if you have this little one. If you glue on a cap here, you can just contract this in. So these are the same.
So it's non-commutative.
It is commutative.
It is commutative. Okay.
Yeah. Yeah, because this is like a twist. But just kind of okay. So what he was saying, this is the part that when I found it, it made me really happy, and I told everyone about it the next day. If you call these circles like ABC. And when you glue on this thing, when you glue a pair of pants onto A and B, A times B. So you glue a pair of pants onto A and B, you get A times B. Then this says that A times B times C equals A times B times C. And this says that A times 1 equals A. This says that A times B equals B times A. Does that make sense?
What is this, so you're using topology to explain basic algebraic properties?
So these algebraic properties just so happen to be the properties that these surfaces exhibit. So that's if you take this pair of pants, it just acts like multiplication. It's not like I'm not using the pair of pants to explain multiplication, or really multiplication to explain the pair of pants. They just happen to be the same thing.
Wow, that's really interesting.
Yeah.
Also, what about that symbol right there? Not this squiggly line with the two lines below it, but the squiggly line with one line below it.
Sorry, that was like same here. Okay. And then here comes the part.
So can you explain the identity one time? Like why can you just make that a yeah?
Yeah. Okay. Here, I think I just drew it poorly. Let me draw it over here.
Wait, is that one part closed or?
Yeah, there's like a little cap on it. Oh, you see it now?
No, it's okay.
Yeah, I didn't draw the.
So what you're showing is 1 times 8.
I'm sorry, what?
You're showing in 1 times 8. That means
Oh.
8.
And then if we want to be proper, right, so it's a two-sided identity, right, and do the other one, but it's, it follows from commutativity too, then it works on both sides. Okay, but then we have this little delta, or the upside down pair of pants, and this is why we distinguished it. Because this, multiplication takes two things and gives you one thing. This does the opposite. It takes one thing and gives you two things. And they're duals to each other. So this is an algebraic structure that is very difficult to work with. It's called a coproduct, and you have a comonoid. It shows up in algebraic topology, but maybe not so much other like kinds of algebra. I don't think algebraic geometers study it, for instance. And one of the big difficulties is how do you write out what this does? So this is easy. You take two things and then you kind of pair them. You put something between them and you say these are one thing now. Here, if you call this A, what should this be? Right? Yeah. Okay, maybe you say A goes to B and C. But then you have to like pair them together. So there is some notation for this. And I have it here in my notes. I'll write it on the board and then I'll explain that. If you take all these pictures and you flip them upside down, so I'll do that for this first picture. So this is if you flip this picture upside down. You do that for all these pictures, the same things are true. So that says if this is a multiplication, then this actually is a co-multiplication. So if this is an algebraic structure called a monoid, this is actually an algebraic structure called a comonoid. So it tells you that all the things work out. And just like we have these properties here, so this is the first one. This is co-associativity. So if you take some circle, and you apply delta to it to glue on a pair of pants. And then on this first circle you do nothing. And on the second circle you glue on another upside down pair of pants. And then this is the same as if you glue a circle, or if you glue a pair of pants onto a circle, then glue a pair of pants onto the first one, and nothing onto the second. Or, yeah. So this is how you read this. This little times says do this to the first one, do this to the second one. So then you can write all these in dual language. So I'm gonna. Oh, and then this one, this little epsilon, is called a co-unit. And I don't know if this is the case. When I saw this, I thought it was like epsilon. It's sometimes called an evaluation map. Because if you're doing this, say, if you have some kind of like linear algebra added in, so you don't just have comonoid, you have coalgebra, then this takes a vector and gives you a number. So it's an evaluation, it's like some kind of function. Okay, so if you look at these surfaces, they have this like underlying algebraic structure. But really they have two structures. They have this multiplication and it's dual. And then, okay, the dual, you just flip everything upside down and you get the multiplication again. So they don't only have one, they only have the multiplication. So what was the point of doing this difficult thing, right? Well, the point is that these are not two distinct non-interacting structures. They interact in one way, and it's this.
Is it what you drew over there?
Not really. But that is, I mean, they interact, you can't glue them together. But it's this. So if you have something like this, you can bend it. The way you see this is, if you take these two ends, and you kind of straighten them out, you get something like this. And then you just unstraighten them the other way. So, wait. I think I've drawn the wrong thing. Sorry. Sorry, it's this. So you just, pull these ends like that, you get that. You straighten out like this. But another way to see it is, you've had these two things and they just slid past each other. So this is also called a handle slide. And this handle slide is where all the things come from. So if you glue anything together, so you glue these together to get some picture, then, because you can slide these past each other, you can assume you start with some set of circles. And then if anywhere along the line you had something like this, where it splits into two, or where it splits into two first, and then eventually collapses into one. Then you can just slide that down and put all these pairs of pants at the start. So then, okay, you're making some surface, you're gluing it together, and because of this little handle slide, you can start with all the pairs of pants that you're gonna have. And then say, the only problem is if they glue on directly like that. So then you have all the ones that don't glue on directly like that move to the start, and then you have some in the middle, glue together to make a little circle, and then you close it at the end. So this is what all surfaces look like. They you have just like tree roots. Some holes in the middle. And then tree branches. And then if there are none of these, then you just have holes in the middle, and you have the classification of surfaces. So this is the new proof of classification of surfaces. The theory behind this is called Morse Theory, if you're interested. Professor here, Professor Milner, wrote the text on it. It was, so you can get it free online, Milner's Morse Theory. And then a lot of this handle slide stuff, these are called cobordisms. So they were a major topic of study. I mean, they still are. And the first part of his book, Lectures on the H-cobordism theorem, has this. And then people really liked Morse theory. I mean, I really like Morse theory. Yeah, I wanted to do a Morse theory proof of this basic result. So that's a lot of modern geometry is based on generalizations of Morse theory. So then if you do things this way, and then you read like a new paper, you can like really see the like connections. So it's like a really great thing to learn. You know, this is nice, right? So you got the classification of surfaces. But then also, you have this algebraic description of surfaces. So what this is describing is it's called the 1-1 cobordism category. So cobordisms are just this. So you have a circle and two circles, and they're the common boundary of something, so they're cobordant. So the 1-1 cobordism category says you have these one-dimensional things, some disjoint union of circles, and you look at all the ways of gluing them together with this thing. The 1-1 cobordism category is, say, Frobenius bimonoid, something like that. Whatever the structure we just showed is. So you have a complete algebraic description of these surfaces, which is great. That was, you know, why I started this. I was very happy to tell everyone, right? But then there's another step, right? So in physics, a lot of the times, you think of particles as like, so you have a particle that lives on a circle, and you want to describe its state. So in physics, everything lives in like a vector space because it's easy to work with. So then, what you do, if you want to describe some kind of physical theory, you can do this. You start with some collection of particles that live on circles, and you attach a vector space to every circle that describes its state. You have this. And then you do some stuff and say you want to tell the end position. So how will their states change based on what happened in the middle? And then if you have a great, very easy to work with thing called a topological quantum field theory, it only matters what the topology of this is. So sometimes it matters what the lengths are, or like what the more precise structure is. But here, it's great, because it just matters, say, how many roots, how many holes, and how many branches it has. So then you get that it comes from this. So the way you would describe a topological quantum field theory is you assign to a circle some vector space V, and then for this, some linear map from V to V tensor V. And then for this, some multiplication on V. For this, you have, if V is like say a real vector space, you have a one-dimensional map from, or you have a map from R to V, and then this is a color here. So then if you assign this data to all these things, so some space of states for your initial particle, what happens when two particles collide? No, what happens when one particle splits into two? What happens when two particles collide? When a particle is created or when one vanishes. Then you can describe what happens in this physical system. And then this structure we found, this Frobenius bimonoid, very exotic algebraic structure. Then we get that our topological quantum field theory also has this structure, because you just get it by gluing these things together. So then you just kind of add that, instead of working with a circle, you're working with a vector space. So you can like add and stuff. And then the end result is called it's like a vague thing, so I'll write it. Frobenius algebra. And then the statement is that two-dimensional topological quantum field theories are the same as Frobenius algebras. And everyone who works in this field of topological quantum field theories knows this result, but it's called like a folklore result. So it hasn't been like really published. Maybe somebody's posted an explanation online or something. But if you want to work in the field, you just kind of need someone to explain it to you. So now you guys can like work in the field. It's been explained. You now know this result. It's like this construction of gluing things. So there's like 10 minutes left for questions. So besides that, yeah.
So what does happen if you have that situation that's over there?
Here?
Yeah.
Oh, this.
Like how do the dual and the product interact there?
So this is called an intertwiner, I think. This entirely describes the theory, I think. If you assign what happens here, then yeah, it has the same data. So if yeah, so you're somewhat free to assign what happens here, but then once you assign it, I think that determines the rest of the theory.
So like what vector space interactions happen at the boundaries and stuff?
Yeah, so you get what this is. It's you get this composition, which is just a linear map from V to V. And then it can be really any linear map. Yeah. Any other? Yeah?
So if I'm not mistaken, that surface that you drew with the roots of all vector spaces and then the hole in the middle and then the outward stuff, so that surface represents it could represent a system of particles represented by vector spaces?
Yeah.
So what exactly do you mean for the 1 and epsilon case? Because you said it represents a particle like appearing or like being formed and disappearing. Does that mean it appears within the system that we defined, or like what would that mean physically, as we define it?
Yeah, so sometimes particles just get created, like light, right? You have this electron that gets excited and then disappointed, shoots out a photon, so a photon gets created. So if you want to like describe what happens to the photon, maybe it gets created, it's a little cup. Maybe somewhere in the universe an antiphoton gets created, or then they collide and annihilate each other.
Okay.
So this would be the physical, but then we see that this is just kind of like a sphere, and then this, you start with a vacuum and you end with a vacuum. So this is just it's maybe called like an excitation of the vacuum. And then the idea is like, it really shouldn't change things. So you can like kind of get rid of all this stuff. But it's important that you have it.
So you can essentially change that first drawing with the 2 cups and the 1 cup on top and morph that into the sphere without change or like violating anything?
Yeah.
Okay.
The problem that happens is if you have like another hole in the middle,
Right.
then something truly interesting can happen.
Okay.
Any other questions? Yeah?
Is this vector space the space of states?
Yes.
Quantum mechanical system.
Yeah, it's supposed to be. But so like classically, you would think of this as being some infinite dimensional Hilbert space, right? That can't happen here. You have this duality, right? You can flip the pictures upside down. So then you should be able to flip the vector space pictures upside down, which is the statement that the vector space is isomorphic to its dual, which is equivalent to the statement that the vector space is finite dimensional. So you take some, like physicists don't really work with these one-dimensional quantum systems because nothing is really like this. The interesting stuff happens in like maybe 2, 3, and 4 dimensions, but those pictures are actively being studied and they're like completely, beyond, I can't do them. So this is just an example to like what your appetite. But it's like a finite space of states.
So this applies not only to string theory, or because all these pictures remind a lot of string theory, right?
I think it's very related, right? So, these are topological quantum field theories. But like the main ones that are being studied, I think, like people here study them, like Professor Kirillov, this is what his work is in. Study, I think they're called Witten type, after the string theorist Edward Witten. So it's like there's a very rich connection, but I'm moderately ignorant about string theory, so I couldn't elucidate it too much. Any other questions? Yeah?
How would this, you made a couple references to linear algebra throughout this. How would a lot of this stuff relate to linear algebra? I can kind of get the relation off from BDB. That implies that it's, you said it was a linear map, so from BDB, so that implies that it's an operator right there. An operator is a linear function from a vector space to itself. So what other references can you draw up with and how it relates to linear algebra?
So the main picture is this underlying, this cobordism category or whatever.
Mm-hmm.
And then the vector spaces are just what physicists use in practice. So they're not an essential part of the picture. And you could choose other things. So this is called like a linear representation of and they're very important because linear algebra is by far the easiest kind of algebra. So like if you can make something linear algebra, you should. But there's it doesn't follow immediately from the surfaces. It's something we chose, and then we get that instead of a pair of pants, you get multiplication, like an actual like algebra structure. So it's just easier to work with. But there's I don't know of anything really beyond. Anything else?